Art.
So let me introduce Julia, in case you guys don't know Julia yet. Julia Zaini ولا
Zini.
Julia Zini has been our TA for the semester. How many of you have met Julia outside of class? I know she came to class. Well, very good, a lot of people. So Julia is an expert in reinforcement learning. She had done her master's in reinforcement learning, and she's currently doing her PhD with some reinforcement learning. So she's definitely an expert, and she would be a great person to talk to us about what is reinforcement learning. So without any further ado, the floor is yours.
Thank you. Thank you, Dr.
If you have any
Hazim.
questions, remember, this is interactive, so you can ask just like in a normal class.
Okay, thank you, Dr. Hazim. So today's lecture is just an introduction to reinforcement learning. We will just learn the easy method or the introductory methods to reinforcement learning. We'll start by motivation to the problem, and we will learn how to formulate, if we have a certain problem, how to formulate it as a reinforcement learning problem. And then we will learn the methods to solve Markov decision processes specifically, focusing on value-based methods. So first of all, we all know that we have three learning paradigms: supervised learning, unsupervised learning, and reinforcement learning. And reinforcement learning is very important because it's the hope for true artificial intelligence. It has immense potential to solve high-dimensional problems, and it imitates the way decision makers or humans think of certain problems. We see reinforcement learning partially in self-driving cars. We see that in 2017, the AlphaGo, which is a computer program based on reinforcement learning, defeated the world top player in the game Go. We see reinforcement learning in Atari games, in solving complex cognitive tasks like matching a cube with a certain image. We see humanoid robots walking, jumping, and running. We also see reinforcement learning in complex finance tasks, which are basically decision-making tasks, and other complex cognitive tasks. So first of all, we know that in supervised learning, the supervised learning model takes as input x and outputs a certain vector or scalar y. And to learn this model, we have to input to the learning algorithm pairs x, y, and the learning algorithm will output the model, which takes x and returns y, right? مظبوط? For unsupervised learning, the input is x. However, the output is not specifically a regression or a classification problem. We could output embeddings. We could output clusters in case of the clustering algorithms. And for the learning algorithm, my input is the features or some meta information about the data that I have. And the learning algorithm will output the model f, which given x either inputs a new embedding x2 or outputs the cluster number in case of clustering. In reinforcement learning, my model observes a certain environment, and it has a current situation, which we call in reinforcement learning the state. And the output of my model is what action to take given the current situation. And now, how do I learn this model? What should I take as input to my learning algorithm, and what should I produce? And this is what we're going to learn in today's lecture. So as a definition, in reinforcement learning, we have a decision-making process. And the main component of this decision-making, the one who will make the decision is called the agent. And this agent observes a certain environment and takes the best action given the current situation. So when do I cast my problem into reinforcement learning rather than supervised or unsupervised learning? I should have these criteria. I should have a continuous stream of input. So I'm interacting with an environment. Whenever I do an action, I receive another input. Whenever I do an action, I receive a different input. So I have this interaction. And my task is to select not just one action, to select an action at every state. Whenever I move, I need to select a new action. Whenever I select a certain action, it influences the next or future states or situations that I will encounter. And my goal will be to choose the best actions that maximize a certain cumulative or total reward. Finally, and this is very important, I don't have a supervision. So there's no one who's telling me this action is right or this action is wrong. I just know a certain number that tells me how good my action is, which is called the reward and the reinforcement learning. So I have two main steps whenever I'm dealing with a reinforcement learning problem. First, I need to formulate the problem, and this is very important. Choosing a correct reward function or a good reward function influences my solution. Choosing the state, the action space, and so on. So I need to formulate my problem, and I need to choose a convenient solution for this problem. So we will start by how to formulate the problem, and then we will go to how to solve these problems. Okay, so this is the agent we talked about. We have the agent, which is the decision maker, the main component that makes the decision. The agent observes the environment around it. The agent knows the current situation, so I know for sure where I am and what's the situation around me. I know what are the actions that I could take given this situation, and I know some reward information. So I know that this action gives me somehow higher reward than this action. And my output would be the best action to take given this situation, right?
Before you move on.
Yes.
This I think is, could you go back? That slide actually is probably one of the most important slides for here. Because if you remember the earlier slide that Julia was explaining about what is supervised, what is unsupervised, what does it take as input, what does it produce as output. So for us, we've always looked at, if you remember that figure from the beginning of the semester where we have data going in to learn, it produces a model, and then the model has input and gives an output, right? So there's data, learning, model, then the model gets used with new data to produce output. This picture actually represents the lower part. This is where I have input, I have a model, and I have an output. And so this agent here, which is actually our model, you think of it, this has the model in it, and it's taking 4 kinds of inputs, not just one. Before we used to have just X data. So here we have 4 kinds of input that comes into the agent, and the output is not a prediction, it's actually an action, a decision of action that they have to take. So just keep that in mind. This is actually, if I were to put a star on slides, this would be, I will stop again when I come to another slide that I think is very important. But this definitely is, what is the reinforcement learning from a model perspective? It takes these inputs and produces this output. Clear? Questions? Ahmad.
The reward information, how do we determine what they are?
Julia will get into that.
Yeah, we'll do an example on this. Yeah.
Julia will go through these details, but I just want to, the reward is actually something that you have to decide. Every action is a reaction. So that's the reaction, the reward that actually tells it how well it's done with that action.
Yeah, we'll come back to this slide once we formulate our reinforcement learning problem. So now, the dynamics of reinforcement learning. Let's say we have a discrete time domain. So I have at a certain time step t, I am in a certain state S of t, and I know what the state is. So I know that I am in state st. I choose, according to a certain criterion, I choose an action A. This action transitions me to a new state st plus 1, and this transition has a reward with it, which is called RT in this case. Okay, so I have this interaction with the environment. I give the environment my action, and the environment gives me the next state and gives me a certain reward out of t. This is very important. Do you have any questions? Now, how do we mathematically formulate this framework? Usually, we deal with reinforcement learning as Markov decision processes. So we have this decision making, and we have the Markov condition, which we will see later. So for example, let's take this, this game as an example. I have a 3x4 grid, and I have a start state, so the agent starts in this cell, and I have to reach the diamond, for which I will receive a reward of +1. And I might fall in the fire grid, for which I will receive a reward of -1. So the goal is to reach from start the diamond while avoiding falling in the fire state. So if I want to mathematically formulate this game or this problem, what do I need? What do you think I need? Given the dynamics that we talked about. Exactly, I need to know what the actions are, the reward function, the actual location شو سميناها? The state, the actual situation. The environment, what does it tell me? The states, we have the states. What does the environment tell me? If I'm in a certain state, the possible next states, exactly. So if I'm in a current state and I do a certain action, where does this action lead me? So the Markov decision process is defined by a set of states, we call them X, that live in a certain space chi, a set of actions A that live in a certain state A, and a transition function P that takes three values, P of S, A, S prime. So it takes the current state, the action, and the next state, and it gives me the probability of ending up in state S prime, given that I was in state S and I executed the action A. So this is the model of the environment, if you want. So this is the dynamics of the problem. Clear? I have a reward function, R. For now, we will assume that it is R S A S prime. So the reward of being in a certain state, executing a certain action A, and ending up in state A prime. For simplicity, we can assume that the reward just takes a state. So it gives me the reward of ending up in state S prime, no matter what the previous state was. They're equivalent. Some problems deal with this notation, and the other problems deal with the previous notation. I have to have a start state. So where does the game or the problem start? And maybe I have a goal. For example, in this case, is to reach the diamond or an end state. And sometimes in infinite games, I can just play forever without having a certain goal to maximize the cumulative reward. And finally, we have a discount factor gamma. Why is the discount important? To avoid infinite paths. So in this game example, I could loop forever, and then at a certain step in time, I can reach the diamond. I want like the shortest path to reach the diamond, and this is why I include a certain reward. So the rewards are discounted by a factor of time, gamma to the power t. If gamma is less than 1, then with future time steps, I will have less reward. Clear? So in this case, how can I formulate my MDP, Markov decision process? So what are the states? Each cell in the grid is a state. What are the actions? Up, down, left, right. I have the probability function. Remember the transition probability function. It takes a state, action, and the next state. So in this case, I will have the probability of being in state 1, 1, executing the action right, and the ending up in state 1, 2 is 1. So 100% sure I will end up in state S2. Being in 1, 2, and executing the action, 1, 2 is the state. Being in state 2, 1, it should be, and executing the action up, I will end up in the same state, لأنه I have a wall, right? The reward function, the reward of state 2, 4 is -1. The reward of state 3, 4 is 1. And the rest of the rewards are negative. Why do we have negative rewards? Exactly, it's kind of discounting, so I don't want like infinite paths. The start state is 1, 1, and the goal is to reach 3, 4. And the discount, I could choose any discount between 0 and 1. Now, what's Markov about this problem or about reinforcement learning in general? So I assume that the probability of ending up in, yes?
Can I just, can you go back to the
Yes.
slide just 1 second? What I want to mention here, again, I'm trying to draw analogy to what we have seen before. We have seen a model, and the model has data in and then prediction. And the data could be features, or if we're using deep learning, it takes all of this. So here, instead of talking about data in, we have these things that go as input. So you have to define, instead of the data itself now, it becomes the state, the reward, the environment, the probability of transition, the gamma factor. All of these is what we define as our input. So all the discussions we used to have about, okay, if I have to predict the price of a house, I should take the width and the depth, and then maybe the product of the two, the area. That discussion is very different here. Okay? When we talk about input to the model, we're formulating the problem very differently. We're thinking about where am I now, and how do I formulate where am I now, and where could I go, and what's the rewards of making such actions, and then what would be the probability of such motion. So all of these things actually you would need to define to work with reinforcement learning. This would be your input, and your output would be your action, and then it goes through that cycle model that Julia showed earlier. So far we're just defining what the input is and what the output, and then we're going to see later how do we learn a model and what does a model mean in the context of reinforcement learning. Okay. Any questions? I just want to make sure we have analogy to what we've done before. Does this help? Make sense? Or you guys are on it anyways? Okay.
Okay. So you took a hidden Markov model, HMM, in class? Okay. So Markov property tells me that the probability of being in state st plus 1, given that I was in state st and I executed action at, and previously I was in state st minus 1, executed action at minus 1, and so on till I was in the start state, I executed the first action, is equal to the probability of ending up in state st plus 1, just given that I was in state st. So Anna, if I'm now at this state and I executed a certain action and I reached this state, it doesn't matter the history doesn't matter, the previous states. It just what just matters is the previous state and action. Okay, so given this formulation, what is my goal now? To produce? Maximize the reward. And what do I output? Exactly. What are the best possible actions that I can do in every state to reach the maximum reward at the end? And to formalize this decision process, we introduce what we call the policy. So the policy usually takes as input X and produces as output A. And I have to learn this policy. I have to learn this function that takes X and returns A. And we call this the policy, which is a mapping from the state space to the action space. Now, you understood the policy. It's very important. And this is my unknown X. This is the thing that I want to optimize for.
This is the model. So before, again, when we say model, let's say for classification, we want something that you give it X and you can predict the category. For regression, it takes X, it wants to predict the number. Here, that model actually is called a policy, and its job actually is to make an action, decide on the action. So it takes all of these inputs that we just talked about, and somehow it gives you output as an action. So this is the model now. How does this model look like? We are yet to see. How must have be classification, and then we can do logistic regression, decision tree, and so on. So the policy here, could have different forms, but the main thing its job is to do is actually take the states and give me an action. Obviously, with all the other considerations in mind, the reward and all this stuff. Okay.
Clear?
This is the second, I would say, star to keep in mind, because this is the model description right here.
So if you read reinforcement learning problems or you deal with real reinforcement learning, if you read reinforcement learning papers or you deal with real reinforcement learning problems, you will not deal probably with this policy that takes X and return A, because the environment around us is not deterministic. There is no guarantee that if I execute a certain action that leads me to a certain state, there is no guarantee that I will end up in this state. So we deal with stochastic environments. Usually we have the policy as stochastic policy, which we will see later. So back to the star slide. Now I have the agent. My current state or situation is modeled as the state space X and the current state X of t. So this is one input. Another input is the set of possible actions. What can I execute as actions? Another input is the environment information, which is modeled as the probability function, as we saw previously, which tells me what's the probability of ending up in a certain state, given that I was in a certain state, I executed a certain action. And I have the reward information as input. And what's my output? No, not X. The policy, pi. And from...
This is the learning process.
Yes.
This is now the learning process.
And my policy pi, if I know what pi is, then I will know what action to execute at each state. So from pi, I can deduce the best action at each state. Clear? Clear? Okay, so this is an example of an optimal policy. So the optimal policy would tell me, if you're in this state, go to the left. If you're in the state before, just go to the diamond and grab it. If you're in this state, do not go to the right, go up, and you have a higher probability of reaching the diamond. Okay, if you're in this state, one policy could give me go up, another policy could give me go to the right, and I can reach the diamond with this path. Okay, so there are more than one policy. There is an optimal policy, and for some problems there are more than one optimal policy. Now to the stochasticity that we talked about. In deterministic environment, if I say go up, then the agent will 100% go up. In stochastic environment, if I say go up, the agent has a probability of just going up, has another probability of going to the left, a probability of going to the right. And because I have the stochasticity, I can't deal with a policy that takes X and just returns A. It's better to have a policy that takes a state and an action A and returns what's the probability of taking this action given that you are in a certain policy. So now my policy would give me for each state a set of actions and their probabilities. And I would sample and choose an action according to my random variable that I sampled. Should I repeat?
Yes.
Okay, so in deterministic environment, I have a state, I just say, take this action. In stochastic environment, because if I say go up, the agent might not go up. So I would say go up with a probability of 0.9 and go to the right with a probability of 0.1. And the agent will sample a certain number, will draw a random number. If this number is higher than or lower than 0.9, it will go up. Higher than 0.9, it will go to the right. So to introduce this stochasticity into the problem. Question? Yes?
When introducing the stochasticity, why don't we sample the rewards as stochastic, not the action? Isn't the action something that we can think of?
The reward is deterministic. Once you reach a certain, you will not get the reward unless you reach a certain state. So the reward itself is deterministic. Okay? There is something that's called the value of a state. It's somehow a reward. We will get to it. I think it will answer your question. Yes?
When you said that we have a certain probability of ending in any one of these states given an action, I expected us to have a policy that would take maybe the desired action to tell us in which state we might end in. This is what the 0 and 1 represents, right?
0, 1 is the probability.
Of what?
Of executing a certain action given that you're in a certain state. So the policy will now tell me probability of being in this state and executing action up is 0.8. This state and executing action, stay at your place, for example, is 0.1. So it will give me an option to stay at my place or to do another action that might not lead to the optimal solution, but with a certain probability. You will see an example.
The analogy, to think about, let's say we're doing classification. Okay, we have two classes, 1 and 0. So one way to think about this classification problem is that the output is either class 1 or class 0. But we've seen, it's not always that black and white. It's a probability, 0 point something that it's class 1 and 0 point something that it's class 0. So it's not, things are not just totally always black and white. So the same thing with actions. I mean, it's not, I'm not going to take a deterministic action that's going to be up, right, or left. I could be taking any one of those with certain probabilities. So if you tell me I'm telling you there's a potential of taking an up action, it won't, in stochastic environment, in the random environment, I don't always take it. There's a probability that I will take it, but there's also a probability that the agent may take a different. Now, in real world, you can think of a robot actually, يضرب بالحيط, or whatever, حب الهواء وراح يمين. There could be random things that actually force the action to be random, not be just always, my intention is to go straight, but it's not always probable that I will go straight. There's other options as well.
It's just that I thought that the probability would be on, after taking a certain action, to end up in a state. But here we got the probability to the action itself.
Yes.
Right.
We will see an example. It will make things clear. Okay, so a stochastic environment could be, given a certain state, going up will reach to the up state with a probability of 0.8, right 0.1, left 0.1. Now, with this constraint now, if I am in this red state here, going up will reach to the up state with a probability of 0.8, but I have a probability of 0.1 to end up in the right state, which is in the state to the right, which is the danger state, right? So now, what would my policy say? If I have a deterministic policy, then my policy would say go up, right? But I have a probability of falling in the danger zone. So I have more than one option. Is it better to go up anyways? Is it better to go to the left and have a probability of 0.9 or 0.8 of staying at your place? Is it better to go down and go to the diamond using the longer path? So I have more than one option. And this is where the stochasticity of environment is introduced in my learning problem. I can't have a deterministic policy, right? So I need a quantization. Okay, another question. What if the probability of slipping to the right is 50%? Then probably I wouldn't go up if I have a probability of 50% of falling in this danger zone. Probably the best way is to go down and go all the way to reach the diamond. So it's a combination of the reward, of the probability function, of the discount factor. It's a combination of many components of this reinforcement learning problem. So basically, I need a quantization of how good each state is. I need a number that tells me this state is 0.9, this state is 0.8, then I would go to that state with solve it yet. But the policy would be stochastic, so my policy would be policy of 2, 3, 1 is a certain number, policy of 2, 3 ma down is a certain number, policy 2, 3 ma right, and so on.
So it's not 0.1.
0.1 given in هيدا 0.1.
Yeah.
No, it's not related. We need to solve for it. And we will see what are the methods, what are the different methods to solve. Okay? Yes?
Probability 50%, for example, where may it come from?
From the dynamics or the physics of the robot itself. So if you have a good robot, probably if you say go to a certain direction, it will go. If
How do we know the number? The probability value.
From sampling. Yani you would tell the robot go up, go up, go up 100 times, and you will count how many times did the robot actually go up, how many times, and you
you showed in the beginning?
Yes, this is a transition, yes. Sometimes it's given for you, but if you're designing your reinforcement learning problem, sometimes you need to sample yourself or to take into consideration the physics of the environment.
Is it a model, a function, or?
It could be a model. You could have it by sampling. So for example, if you have a certain robot, maybe the transition function, given that the robot is on the carpet, is different than the transition function if the robot is on ice, for example. Definitely it's different. So you would sample or you would take the friction into consideration. This is a modeling problem or a physics problem. It's different. Okay, so for now we assume and we have it and we deal with it. Any questions? Okay. So now we need to solve this Markov decision process that we have. The optimization function that we're dealing with is the following. I'm maximizing a certain number, and I'm finding pi, the policy, that maximizes this, whatever you call a loss function in other learning paradigms. So I have a certain loss function. I'm minimizing the loss function, maximizing the inverse of it. And I'm finding pi that maximizes this function. What is this function? We need to maximize reward. It's not a reward at one step. I want to maximize the cumulative reward. So I need to maximize the summation of the reward from t equals 1 to the maximum number of steps. It could be infinity. It depends on the problem. So I'm maximizing this summation of the reward at each time step. And I have this discount factor, gamma of t. So I'm maximizing the summation of the discounted rewards. 1 over t, لأنه we're dealing with average, it's a constant. And I'm introducing the expected value. Why I'm introducing the expected value? I have stochasticity. So I have probability in this reward itself. I have a probability. يعني, if I say that the reward at this state, it could be with probability 0.9, it could be A. With probability 0.1, it could be B. So my expected reward would be 0.9 times this reward plus 0.1 times B, right? So because of the stochasticity, I have to introduce this expected value.
Shouldn't the expected value be inside the summation?
I think it's the same. Mathematically, it doesn't matter.
But if we have a different probability of ending up in different places, in different states, would it also be the same?
I don't think it matters because the expected value is a summation and this is a summation. You can interchange them.
Sorry. And gamma, what is gamma?
Gamma is the discount. So the reward at time step t should be higher than the reward at time step t greater than t2. Remember the slide? Okay, to avoid infinite paths.
Okay, but if we are taking the expected value of the sum of these, where do we put the probability term? The probability for each reward, actually there is a probability.
Exactly. So the reward, if I am in this state, the reward could be, and I will go to this state. With probability 0.9, I will reach this state, and I will have a reward A. And with probability 0.1, I will reach another state, and I will have a reward B. So the reward at this time step would be 0.9 times A plus 0.1 times B.
This would be the value R here?
This is R, exactly. Now gamma, if this is the first time step, you multiply it with 1. If this is the second time step, you multiply it with gamma. Third time step, gamma to the power 3 or 2, whatever. Okay? Clear? Now, to solve this problem, I have 4 different methods. I have the value-based methods.
Can I just,
Yes, sure.
now that you've explained it, can I just, again, before we go into these solutions, this is another very important, before we go into the method, this is a very important description here. What is the equivalent of this when we talked about supervised models or unsupervised models? The objective function, exactly. So with the objective function, we used to represent the model by parameters, theta, and we say, what are the parameters of all possible parameters, theta, that I can find? which one of them will minimize, in that case, the loss function. The objective function was a loss. If it was a gain, we would have said, of all possible parameters of data, which one would maximize the gain? So this here, because we're talking, the enforcement learning is formulated as reward. I'm, 100% sure you can formulate it as loss, and instead of saying maximize reward, minimize loss. Same concept. But this actually is exactly the equivalent of what we did when we wanted to find the parameters of the model to minimize an objective function. You find the parameters of the model, which now is the policy pi. What is pi? What are the rules? What does it, what should it be so that I maximize my reward? Okay? So the objective function here is the sum of all possible rewards that I can get by following a certain policy. Okay? Clear? This would be my, third star of the slide, or fourth star.
Okay. So I have 4 different methods to deal with such maximization or optimization problem. I have the value-based method. In the value-based method, I compute the value of each state. The value tells me how good the state is. And then my policy would say, go to the state that has the highest value. The policy-based approaches. So this is an optimization problem. So basically, it's a fancy way of saying maximize f of find x that maximizes f of x. In math, how do we do that? Exactly. I get the derivative f prime of x equate to 0, find x that is the solution of f of prime x is equal to 0. So now, because we don't have a one-dimensional problem and we have a more complicated problem, we do something like the Jacobian and we derive this optimization function, and we get the policy, which is a function that maximizes this function without computing the values, by just deriving and going to the local minimum and so on. The actor-critic methods are a combination of both methods. We compute the value of each state, and we use these values to critique the policy and to update it. So we have a value and we have some kind of policy, and we're doing the combination. And finally, we have model-based, which is not mentioned here. The model-based methods, like I said before, whenever we want to model the environment that we have to get the transition probability function and so on, we use model-based methods. And model-based method can be integrated with any other MDP method. Yes. No, the reward is the reward that you will actually get. The value of the state is somehow the expected value of the reward that you will get given that you are in this state. Because I have the stochasticity of the environment, then I will not for sure get a certain reward, a certain number. And we will see how to compute the value of the state later. Clear? We will start by the value-based methods. So if this is the same grid as we had before, we have the +1 here and the -1 here, and I have all these other states. So if I have this map, I know that the value of this state is 0.48, the value of this state is 0.28, and the value of this state is 0.43. Then 0.48, then 0.43 I will go to the left. لأنه this state has a higher value of the state on the right. Yes? We will see. Okay? So this is just to tell you, if I have these values, then my life is so much easier. Yes?
The state can be, like, we can reach state for different states. Is that the same value? We get the same value. I can reach it for the right.
Okay, because we have the Markov property, the reward of this state is not cumulative. It's just the reward that I will get given that I am in the state and for future steps, not for previous steps. We will see how to compute it. Okay? And these arrows here, what do they represent? I'm looking for a specific word. مش actions. Policy. So the arrow would tell me if you're in this state, then go here. This arrow would tell me if you're in this state, then go up. So this is a policy which is deterministic. It's not, in this case, it's not stochastic. Or it could be stochastic, but we're just visualizing the arrows with highest probability.
Can I just, I think just pause a picture.
Sure.
Is it clear, if I were to ask you what does the policy mean here, what would it be? How would you describe the policy here? What is it?
The action at the state.
Close.
That takes me to a state with higher value.
It's actually, I mean, maybe the close. It's the set of actions wherever you are. So it's kind of giving you the rules. If you are in this position, this is the action to take. If you're in that position, this is the action to take. So this is why, I mean, these arrows show you. If you're in that cell in the left corner, it's telling you the action to take would be up. If you're in the cell at the way top, this would be the cell. So the policy is not just about one particular location. It's the rules for all of it. So it's the model that describes everything, that we would possibly do, given an environment and given states and so on, and the action that we have to follow.
Okay. I have a question. Why do you think we have the arrow in this state to the left? It's closer to get to the right and then go up and then grab the... Why do I have a higher value in this state?
Danger.
Exactly. So this danger here, affected the value of this state. Definitely it affected the value of the state. So it affected the value of the state, and I can reach the state from the state and so on. So now it's better, given the reward function اللي هي هون and the transition probability and whatever, it's better if I'm in this state than go all the way up and then try to reach the diamond. Yes?
I thought you said that there's no stochasticity.
No, I said the policy here seems to be deterministic because at each state I only have one arrow. And it could be stochastic, and we're just showing the arrow that has the highest probability. The environment is stochastic, but the policy could be deterministic. Okay, so the environment is stochastic, meaning that if I'm in a certain state and I executed a certain action, there is no guarantee that I will end up in a certain state. Deterministic environment means that if I execute a certain action, I will 100% sure and know I will end up in a certain state. This is the environment. The policy, deterministic policy, at each state I would give you just one action. Execute this action. Stochastic policy, it gives you a list of actions with their probabilities. Usually, when I have a stochastic environment, I will have a stochastic policy. Usually. Yes?
Rewards, how are they determined?
Sorry?
The rewards, who determines them, or when do we determine them?
When we?
Determine them. Like the value.
This is, okay, in this case, this is a game. So the designer of the game would tell me, no, if you go to the green state, you will have a +1, red state, you will have a -1. If you're dealing with another problem, then probably you would design your reward function yourself.
So we are responsible for designing the reward function.
It depends on the problem. There are some heuristics that you can depend on. For example, usually the distance to the goal or the inverse of the distance to the goal could be a possible reward. For the distance, you could have Euclidean distance, Manhattan distance. So how do you design your reward function according to the problem that you have? Okay?
Let me give you an example of something that makes sense in physics. Assume you're trying to figure out the best way to run a program on a computer, and the reward could be how much you save energy. So if you have different choices of running that program, and one of them costs more energy, so the reward itself could be the energy consumption, and it's the energy consumption and maybe memory, and so you can use physical things that actually reflect losing or gaining in your reward. Or, like, Julia said, it could be something. So, if you're trying to make decisions on, task distribution or something like this in a computing environment, CPU memory usage, energy consumption could be, reward function that you can use. And obviously, these are losses, so you have to do something, reverse 1 over or something to make them.
I can give you an example for, Alexa by Amazon, the chatbot. Okay, so I attended a talk on how is the reinforcement learning formulation of this problem. And you will be surprised that the reward function is they do speech analysis, right? And from the speech, they get a certain numeric value of how satisfied the customer is. And this numeric, like sentiment analysis. And this numeric value is the reward. So if the user is shouting or the user is angry, I will get a negative reward. The user is happy, I will get a positive reward. And the sentiment analysis module of component of this Alexa gives me the reward. The designers of Alexa designed this reward function. Yes.
So you're saying that when I speak with Alexa, and typically when you speak with the older voice recognition and stuff, and they recognize something silly, you shout at them.
Yeah.
Are they using that?
Yeah. They know. They process it and they know to which extent you're satisfied, and they use this to update if they have online learning, to update their next policies. You had a question.
Let's take Mandy's question, and then there's still quite a few slides, so let's take this question and then we move on.
In this example, the reward is only when reaching the final...
Yes, the reward is +1 for the green state, -1 for the red state, and I think -0.03 for the other states.
Yeah, and this moving to any other, in our way towards the end, there is no reward?
There is a negative reward. مثلا عم تصرف بنزين. You're doing a lot, you have a loss. Okay. Okay, so we introduce what we call the value of a state. The value of the state is the expected, the value of a state given a policy pi is the expected value of the reward that I can get given that I am in a certain state, right? So mathematically, it's the expected value of the summation of the rewards given that my start state is S and I executed the policy pi. Sure. Okay, so it's the expected value لأنه I have the stochasticity of the cumulative reward, and this reward is discounted, conditioned on being in a certain state as 0 لأنه the game starts with as 0 and executing the actions dedicated by the policy pi. Clear? How to compute this value? Clear for now? Yes.
Is this the case of stochastic or deterministic?
No, stochastic. I have an expected value.
And this applies to the slide before?
Yes. If you have a deterministic policy, then you wouldn't you could have the same formulation, but the expected value will just have 0.1 times something.
So it would
1 times something, sorry.
It would only depend on the distance and not the closeness to
No, it's not on the distance because I have a reward function here. It's the reward, the actual reward.
Yeah, yes, but in the slide before...
Wafi, if she goes through some examples, it may become clear.
Yeah. We introduce what's called the Q value. The Q value is similar to the value, but it takes a state and an action A. It's the expected value of the cumulative reward, the discounted cumulative reward, given that I was in a certain state and I executed a certain action and then I followed a policy pi. As an example, the example will make it clearer. The value, this is the value, a map of the values, the one that we've seen before, and this is the Q value. So for a certain state, for example here, I have a value of being in this state and executing up, down, right, left. So I will know what the best action to take from this Q value also. Okay? And my optimal policy would be a maximization over this expected value. The algorithm is called the value iteration, which is one of the most basic algorithms or fundamental algorithms in reinforcement learning. I start with initializing all the values of all the states to 0. And then I start. At each iteration, I loop from 1 to h. At each iteration, I have the values at the previous iteration, and I compute the values at the next iteration. The formula is as follows. The value at the iteration I plus 1 would be the maximum of a certain quantity. Maximum over all actions, over all possible actions in this state. شو هي هذه الquantity? This quantity is the probability of ending up in all the next states that I could end up in. لأنه I have a stochasticity in the environment. So it's the summation of the probability of ending up in state S2 times the reward that I will get if I am in state S2 plus probability of ending up in state S3 times the reward that I have in state S3 and so on. بنزيد عليهم the value of this state S3 لأنه I have a cumulative reward. يعني the reward that I will get from the transition plus the value of this new state that I have. Clear? بعيد بعد مرة?
Actually, this is you can ask now. If it's still not clear, you can ask now.
The R is not discounted.
The discount is on. Okay, so you got R, and the discount is on the next values. I think if you do it mathematically, you will have the same. You will have like gamma on the R, but this is the algorithm. But we have a discount on the value of the next state. Yes.
What is
H, you could set it before, you could have like, I want to do 1,000 iterations, and you can just loop until you converge. And there is actually a theorem that proves that this Q will converge to the optimal Q if my I goes to infinity, with sufficiently large number of iterations. Clear? So let's go to the example. Assume that with probability 80%, I will end up in, if I executed a certain action, I will end up in the desired state. With probability 0.1, I will go to the neighboring states, and I have no probability of going backward. So this is the problem.
I'm feeling bad for me asking a question. So let me see if I can clarify.
Okay, I'll just ask it again.
Yeah, go ahead.
So if you go back to the previous slide, thank you, sir.
Can you go back to the values slide?
Sorry.
Yeah. So if the probability was
one more. I think I was asking this question on.
It's the same slide.
On the value,
Okay.
not this one. On the equation of the value. Yeah, this one.
right. No. Let's stay with the yes. Okay. So if we had a deterministic policy and a deterministic environment, would how would the colors change? So would the value just depend on?
Yes, if you have a deterministic environment, then if you're in this state,
Which one?
this state, it's 0.57, you will 100% go up.
Yes.
لأنه there is no probability of falling in the danger zone, right?
Yeah.
So definitely in this state, you will not go all the way. You will just go right up.
Yeah, exactly. And so the 0.28 would actually have the same value as the one at 0.43 right now, right? 0.43.
Yes.
Okay, that's my question.
Okay.
Exactly.
لا, it's a good remark.
Yeah. So,
لأنه they're symmetric.
yeah.
There is no way I execute the action up here.
Okay, because it didn't make sense that they would have different colors
Yeah.
if it weren't.
Yes. No, this is stochastic. Okay. Any questions? Okay, so we have the transition probability function. We have if the agent hits the wall, then it stays at its place. We have a discount factor of 0.9. And we know that the agent receives a 0 reward for every move, except for the terminal state, the green one, it will receive a +1, and the red one, it will receive a -1. Then at the first, we said, and we initialize all the values to 0, right? For the first iteration. And this is the equation of the update. Let's assume I want to update the value of this state. I will update it by maximum over all actions, and I will consider the action right, and I will consider the action up, of the probability of ending, if I executed right, I have a probability of 0.8 of ending up here, 0.1 of staying at my place, and 0.1 of going up, right? So times this probability times the reward of each of the states. I don't have a reward, and the value of the next states is 0. Then all this P times R plus gamma V S prime will be 0 for all the states. Then the value of the state will stay 0 at the first iteration. Clear? The only two states that will have new value for their new values, the plus 1 will minus 1. The plus 1, I have a probability of up, right, down, or to the right. And I have whenever I am in the state plus 1, I will receive a reward of plus 1. So this value is plus 1. The value of the next state is 0, so it will be plus 1. And the value of this state, it will be minus 1 according to the formula. Now I received a value of minus 1. So this is the first iteration of my value iteration algorithm. Is this enough? Clearly no. For the second value, for the second iteration, definitely I will have the value of these states still on 0. The only state that will be updated is the 0.72. It will be the probability of ending up in state 1, اللي هي 0.8, times the discount, and this is the, I have one هيدا, times the value of state 1, which is 1. This is for action 1. For action 2, اللي هي going down, it would be 0. For action اللي هي going to the left, it would be 0. So the maximum of all these values is 0.72. It will be 0.72. Now, who can tell, is this clear? Who can tell me why the value of this state did not change? هيدا الزيرو اللي حد الأحمر. This one. تطلع either go to the right and have a negative value, or go up. بس go up ليه ما استعملنا 0.72? Exactly, and we're using the V at I. So we're using the values of the previous iteration. So it will be 0. Going down is 0. Staying at the place is 0. So the maximum of negative 0, 0, 0 is 0. So the value would be 0. Iteration 2, I will update this value and this value. Now I use the 0.72. So going up would give me a positive value. So the value of the state will be updated, and so on. After 4 iterations, 5, after 100 iterations, I will have this map. And again, the arrows are the policy. And the policy is to the state that gives me the higher reward. If I have a deterministic policy, I could have a stochastic policy. Yeah, in this case, they took the risk, and we can go up. مع إنه I have a probability of 0.1 of going to the right, to the danger zone. Because of my reward function وكل شيء, طلع عندي the value of this state is higher than the value of this state. If the value of this state is higher, if I have مثلا هون instead of minus 1 a minus 100, then probably the value of the state will be higher, and then the agent will go all the way up ليوصل على الdiamond. Clear? Any questions?
I actually want to make a point.
Yes.
There's something beautiful about this. I don't know if you guys felt it. Remember the discussion we talked at the beginning of the semester? We said, the AlphaGo decays actually, and how does a computer beat, the smartest person? Well, if you think of this as a game, the computer initially had no idea how to play it. It started with values of 0, 0. So if you put a coin somewhere that you want to get to the end, it will say, I go nowhere. It's basically stop. But as it tries to play this game, basically with itself in a way, with this reward function, it was getting better and better at it. And finally now, it finally came up with a policy that actually will be the best policy possible. And this is kind of what, the power and beauty of reinforcement learning, that you start from an environment, as long as you can define the reward functions properly, and you have the right definition of the environment, it will learn with time. Every time, you know, it's doing better at learning policies. You embellish with few things, and then it evolves. And then with time, it will just get better and better and better and better. And if you wanted to have it, you know, quickly learn how to play chess, you let it play with itself. You know, and the reward functions in there could be the losses or shvarfni. You could define how that was. Does that make sense?
Yeah, there's no way the human brain would do these calculations for 100 iterations and get these values and this fast, exactly, and execute the best actions. And remember, this is only a 3x4 grid. This is very low dimensional. In reinforcement learning, with Atari games, we're dealing with high dimensional problems, and reinforcement learning would do a great job with such dimensions. Yes?
Isn't it a bit awkward that if you were on the tile 0.48, the best thing to do is to go up? And if we were on the 0.43, the best thing to do is to go left.
On the 0.48 والتاني شو هي؟
This one.
To the left.
The best thing to do is to go up, صح?
Yeah.
Okay, so بينما 43, the best thing to do left probably because there is the danger of falling. Okay, so why didn't we then, in this case, at 48 go to the left?
48 is very close. يعني with 2 tiles, you'd reach 1.
Can I explain differently? Let's think this is, you know, we're trying to have self-driving vehicles know how to navigate around, right? وانت بسيارة, right? And, you know, there's 2 objectives you have in mind. You want to get there as quickly as possible, but with the least risk, right? So if you go this path, and there are 2-3 steps that you can get to it, but you also have probability تدهور. Imagine this is actually تدهور, right? So there's a trade-off between, think of it this way, between getting there fast or getting there slow, but getting there. So هون يمكن توصل بسرعة بس يمكن تدهور على الطريق. So this is why here versus here makes a difference.
We compensated with the
Absolutely.
Yes. So the path here differs from the other one by يمكن 2 tiles. Except هون it differs by 1 tile. So يمكن صار أحسن له to go with the shortest path and while not avoiding the danger. If I have here instead of -1 a -5 or a -10, maybe it would be different. And command discount factor. So maybe you're discounting more for longer paths. It would differ. Yes. So see, I have the discount factor in the formula. I have the reward, and I have the probability. So all this formulation that I had before is in the formula. You know, I will take into consideration the reward. I will take into consideration the discount factor and how much probability do I have of falling or staying with the right path. Yes.
I didn't exactly get why the 2.85 state is the first one that we learned after the first iteration.
Okay. So the first ones are the +1 and -1. So first iteration. لا, we learned them. كيف بيانوا من هيدا الريورد. So the reward of being in the green state is +1 and كل شيء تاني is 0. Then the value of the state would be +1. Same for -1. هلا هون this to compute the value of this state, I have to go over this formula. هيدا is a combination of the next states. شو هن next states؟ هيدا وهيدا. And both states have a value of 0. Then the value would be 0. It's a combination of 0.8 times 0 plus 0 whatever.
What about the -0.3 the reward?
In this setting, the reward is 0.
Okay.
بينما هون I have a combination of this ending up in this state, ending up in this state.
When?
This is 0.72.
Okay.
كرمال هيك we learn 0.72 next.
الليزر هون كده.
ما كتير عم شوفه. Okay, so in 0.72 it was 0. مظبوط. هلا I have a probability of ending up in 1 times the discount factor. It will appear here and I will have a 0.72. For this state, I have a probability of ending up in this state and I have a probability of ending up in this state. بس the maximum one is this one. مظبوط لأنه هيدي مش positive.
اللي كانت zero.
مظبوط كانت زي بس 0 is greater than negative.
Yes.
So it will be 0. So the only state that will be updated هو هيدا.
So Julia, we have about 6 minutes.
Yeah, I have one slide left.
Yeah, why
يمكن.
don't you just do that last
Yeah.
slide? And
So the state-of-the-art algorithms for the value-based methods and the Q-learning algorithm, deep Q network, temporal difference learning, fitted value iteration. For the policy-based algorithms, we have the reinforce, which is the father of all other algorithms in policy-based algorithms. We have the natural policy gradient and trust region policy optimization. For the actor critic, we have SAC is very well known, and we have the asynchronous advantage actor critic. Well, model-based, we have the DINA and the guided policy search. And I prepared some of the tutorials on reinforcement learning and websites, and some of them are, I think, papers. Yeah, this is a survey paper, this is a book, this is a paper, this is a paper.
And the appendix, you have also more stuff, right?
Yeah, you want to go over them?
We'll just mention what they are.
Okay. So I included slides for the policy search. Personally, I like policy search methods. I did my thesis using these methods. So basically, we parameterize by a certain vector theta, and here we do the derivation, and we get the policy that maximizes this function. Usually, the algorithm is like the gradient descent or gradient ascent algorithm. We start by a random parameter, and we update it at each step by a certain learning rate times the derivative. This is the reinforced algorithm. Okay, this is a very important concept, which is how much can we explore. Let's assume that the reward function is not, the transition function is not known. So I have to go and explore. So now if I know that this state has a reward of +1, I think that this state has a reward of 0.1. بس ما بعرف شو في after these states. Do I actually go to the state that has a higher reward, and then probably I will have a higher reward, or do I explore the state that has lower reward, but probably that will lead me to higher rewards? And this is a very big trade-off, Bill reinforcement learning, that's called exploration versus exploitation. Exploration means and we can play experimental moves to see just how much reward can we get from these moves. And exploitation means that we do the moves that we for sure know that they are best at this moment, regardless of where they can lead us. Yes?
And this is done during training or during play?
During learning.
During learning.
Yes. Sometimes you have online learning, so whenever you output a policy, you go and execute the actions, and then go back and update your environment your knowledge about the environment, your state space, and so on. So it could be both ways, but usually it's during learning. We have the model for the actor critic, and this is an example that can answer your question على reward. So if I was in state B and executed the action east, and I ended up in state C and I receive a reward of -1, بس في محل تاني كمان B east C -1, and we don't have B east مرة تانية. So B east I will end up in C with a probability of 1. بينما C east sometimes I end up with D, sometimes I end up C east D with D, مرة with D, مرة with A. So I ended up 3 times على D, 1 time على A. So my probability would be C مع east with D is 0.75. بينما C east and ending up in A would be 0.25. So this is an example of if we don't know what the probability function, the transition probability function is, how can I learn it? How they Saru advances.
Yeah, so basically, she has placed slides on these different methods that, she covered details on the value-based method, but there's other methods, the model-based and the hybrid models. So, and then these models. So these are more details on those. So for your own reading, and if you have questions, you know where to find Julia. I want to thank Julia tremendously and give her a big round of applause. I think it was a wonderful lecture.
Thank you.
You know, thank you for all the time you put into this. Any questions? Any last questions before we take off?
So in this whole formulation, our reward was constant +1.
Yes.
For example, in a game of chess,
Mm-hmm.
at each step, the other person is doing a step that affects the final reward.
Yes.
So how do we actually, at each step, we need to compute the whole policies, or?
We have two types of policies. We have offline policies and online policies. Offline policies, you learn everything and you produce the best action for each state. Online policy, you see you observe, you do an action. Usually, whenever you have adversarial games, you do an action and you wait for your opponent to do another action, and then you recompute somehow a policy according to that. It depends on the computation that you have. It depends on your formulation. And I don't know current chess games كيف معمولين. So, but it's one of these two.
But you can change the rewards. I mean, the rewards could change. I mean, they don't have to be fixed all the time. And there could be, you know, different kind of rewards. So the reward for, if they take your, you know, the chess haja, then, you know, there could be higher penalty than certain other things, right? So depending on that. So you can have different rewards depending on what exactly gets lost.
Maybe I can answer a little bit your question, because the project we're working on is reinforcement learning with chess in the background. So is your question saying, like, how do you actually evaluate what move to take if there are possible opponent moves afterwards? Okay, this is what is called the look ahead. So when she presented the exploration and interpretation, there's actually another component that's added on top of the reinforcement learning here, which is all about exploring the possible move that you could take and what the opponent could reply, and evaluating the reward based on that.
Exactly. If you have high computational power, then you can do a brute force of all the actions that the opponent can do, and then calculate your next value, and then choose the action based on that. If you don't have a high computational power, then you can't mimic the opponent and know all the possible action, the values of all the possible actions. Then you would go somehow online, you would do a certain action, and then you wait.
Right, like in chess, for example, you can't brute force. Chess is not solved.
Yeah, exactly.
So what they do is that online, after you've trained your policy offline, what they do, the current best players, is that they online they have a searching algorithm. So, for example, the best one, Alpha Zero, uses Monte Carlo research, which evaluates the possible outcomes of different moves from your current position, and then when the time is up, for example, you specify that it can think for 5 seconds, and within the 5 seconds, which it thought it calculates over millions of possibilities, it chooses the best one that maximizes the reward, not knowing if effectively it's going to win the game, but it has a certain look ahead.
All right. Thank you again.
Thanks.
Monday, you guys need to see me. I'll be going out in my hours. Don't let you know.